Hello everyone, this is Deepa from St.Josephs College of Arts and Science for Women, also working as an assistant professor in Department of Mathematics. In this video, we will see what is metric space. Generally, we know that a metric should satisfy non-negativity, definiteness, symmetry, and triangle inequality. First one is limits in metric spaces. Definition, we say that f of x approaches L as x approaches A. If given epsilon greater than 0, there exists delta greater than 0 such that rho of f of x comma L less than epsilon, where rho of x comma A lies between 0 to delta. In this case, we write limit f of x equal to L or f of x approaches to L. If m comma rho 1 equal to m comma rho 2 equal to r, rho of f of x comma L equal to modulus of f of x minus L, rho of x comma A equal to modulus of x minus A. Consider the function f on the metric space M, that is limit f of x equal to L, limit f of x equal to n. Next one is theorem on metric space. Let M comma rho be a metric space and let A be a point in M. Let f and g be a real valued function whose domains are subset of M. If limit f of x equal to L and limit g of x equal to n, then we have to prove the following conditions. That is, first one is limit f of x plus g of x equal to L plus n, limit f of x minus g of x equal to L minus n, limit f of x g of x equal to ln. Last one is limit f of x divided by g of x equal to L by n. Proof of the theorem. We prove only that f of x g of x equal to ln. So since limit g of x equal to n, we have for some delta greater than 0, modulus of g of x minus n less than 1, modulus of g of x less than modulus of n. This modulus of n strictly less than 1. We are assuming this value equal to q, where rho of x comma a lies between 0 to delta. Now consider f of x g of x minus ln. It can be written as f of x g of x minus l g of x plus l g of x minus ln. That is, add and subtract l g of x. In this first two terms, we are taking g of x outside. So g of x modulus of f of x minus L plus L g of x minus N. So taking modulus on both sides, modulus of f of x g of x minus Ln, this is less than or equal to modulus of g of x, modulus of f of x minus L plus modulus of L, modulus of g of x minus N. Our aim is to find what is these two values. So modulus of f of x g of x minus ln, this is less than or equal to, we know that modulus of g of x equal to q. So q into modulus of f of x minus l plus modulus of l modulus of g of x minus n. So given epsilon greater than 0, there exists delta greater than 0, so then q modulus of f of x minus l, this is strictly less than epsilon by 2, and there exists delta greater than 0 such that modulus of L modulus of g of x minus n less than epsilon by 2, where rho of x comma a lies between 0 to delta. Substitute this to equation in equation 1, we get modulus of f of x g of x minus ln. This is less than or equal to epsilon, that is f of x g of x approaches to ln. Similarly, we can prove that limit f of x minus g of x equal to L minus n, limit f of x g of x equal to ln, and limit f of x divided by g of x equal to L by n. The next one is definition of convergent and Cauchy sequence. Let M comma rho be a metric space and let Sn be a sequence of points in M. We say that Sn approaches L as n approaches infinity. If given epsilon greater than 0, there exists n belongs to I such that rho of Sn comma L less than epsilon. In this case, we write limit n tends to infinity Sn equal to L or Sn equal to L as n tends to infinity. That is, Sn n equal to 1 to infinity is a conversion in M to the point L. Next, Cauchy sequence. Let M comma rho be a metric space and let Sn be a sequence of points in M. We say that Sn is a Cauchy sequence. If given epsilon greater than 0, there exists n belongs to I such that rho of Sn comma Sn less than epsilon. The proof of the following point is identical. Let M comma rho be a metric space. If Sn is a convergent sequence of points of M, then Sn is Cauchy. That is, a convergent sequence implies Cauchy sequence. Next, theorem on continuous function. If f and g are real valued function, if f is continuous at a and if g is continuous at f of a, then g composite f is continuous at a. Proof. We must show limit extends to a g composite f of x equal to g composite f of a, or limit extends to a g of f of x equal to g of f of a. That is, given epsilon greater than 0, we must find delta greater than 0. So modulus of g of f of x minus g of f of a less than epsilon, where modulus of x minus a lies between 0 to delta. Let b equal to f of a. Substitute this value. So hence there exists eta greater than 0 such that modulus of g of y minus g of b less than epsilon, modulus of y minus b less than eta. But also by hypothesis, we know that limit extends to a f of x equal to f of a. Therefore, modulus of f of x minus f of a less than eta, where modulus of x minus a lies between 0 to delta. So modulus of f of x, we know that f of a equal to b. So modulus of f of x minus b less than eta. Thus, if modulus of x minus a less than eta, then f of x is written eta of b, and so we may substitute f of x for y into hence modulus of g of f of x minus g of b less than epsilon. This completes the proof. Thank you.